Good day, everyone. Welcome to another modern physics class. My name is Mary Angel Jean Aikaw-Saren from BSED Science 3. And I'm gonna be your teacher for the day. The topic that I'm going to discuss today is related to quantum mechanics, which is Louis de Broglie's explanation of Niels Bohr's assumption about angular momentum. On the previous lesson, which is discussed by Mrs. Kapalad on Niels Bohr's atomic model and the hydrogen atom, she mentioned that there are various postulates on Bohr's atomic model. So my topic is Niels Bohr's second postulate, which is about the angular momentum of an electron. Niels Bohr is a Danish physicist who proposed a model of the atom in which the electron was able to occupy only certain orbits around the nucleus. His atomic model was the first to use quantum theory. In that, the electrons were limited to specific orbits around the nucleus. Bohr used his model to explain the spectral lines of hydrogen. If we follow Bohr's atomic model, we can study the different arrangements of electrons that are located among different orbits near the nucleus. The angular momentum of electron orbiting around the nucleus is quantized. He further added that electrons move only in those orbits where angular momentum of an electron is an integral multiple of h/2, where n is equals to 1, 2, 3, and so on. Mathematically, the formula for angular momentum is mvr or nh/2pi, where m stands for the mass of the electron, v for the velocity, r is the radius of the nth orbit, n is the orbit in which electron is, and h is Planck's constant. Now 2pi is also a constant. The quantization is why should the angular momentum can have only those values that are integral multiple. The question was explained by the French physicist Louis de Broglie in 1923, 10 years after Niels Bohr Proposal. Louis de Broglie. In 1924, he introduced the idea that particles such as electrons could be described not only as particles but also as waves. This was substantiated by the way streams of electrons were reflected against crystals and spread through thin metal foils. De Broglie argued that the electron in its circular orbit must be seen as a particle wave. Let me show you a presentation of his hypothesis. On a string, particle waves can lead to standing waves held under resonant conditions. When a stationary string is plucked, a number of wavelengths gets excited. However, we know that only those wavelengths survive which form a standing wave in the string, which have nodes at the ends. Also, in a string, standing waves are formed only when the total distance traveled by a wave is an integral number of wavelengths. Waves with other wavelengths interfere with themselves upon reflection, and their amplitudes quickly drop to zero. This is a summary of the illustration that I showed you earlier. Louis de Broglie explained the quantization of angular momentum of electron. According to him, the particle waves travel in a chord and have an analogous nature or behavior. And under resonant conditions, particle waves can drive towards the standing waves. If we pull out a stationary string and we pluck it, the excitement of wavelength occurs. As for the findings, it is inferred that the waves that have nodes can survive the angular momentum, and later on, they create standing waves in the string. Now let's move on to the angular momentum of electron formula. Standing waves are formed in a string when a wave completed the total distance of its integral number of wavelengths. That is why, for any electron moving in the kth circular orbit, having the radius of rk, the total distance covered by any electron is equal to the circumference of the orbit of an electron. The formula of orbital angular momentum is given by 2 pi rk is equals to k lambda, where lambda is the de Broglie wavelength. We know that the Broglie wavelength is given by the formula of lambda is equals to h over p, where p is electron's momentum and h is Planck's constant. Hence, lambda is equals to h over mvk, where mvk is the momentum of an electron revolving in the kth orbit. Inserting the value of lambda from equation 2, which is lambda is equals to h over mvk, and in equation 1, which is 2 pi rk is equals to k lambda, we get 2 pi rk is equals to kh over mvk, and mvk rk is equals to kh over 2 pi. Hence, the Broglie hypothesis successfully proves Bohr's second postulate, stating the quantization of angular momentum of the orbiting electron. We can also conclude that the quantized electron, orbits, and energy states are due to the wave nature of the electron. The Bohr's hypothesis provided an explanation for Niels Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron, orbits, and energy states are due to the wave nature of the electron, and only resonant standing waves can persist. Niels Bohr model involved a classical trajectory picture and correctly predicts the gross features of the hydrogenic atoms. Hydrogenic atoms consist of a nucleus with a positive charge and a single electron, where Z is a proton number. Examples of hydrogen atom are singly ionized helium, doubly ionized lithium, and etc. In particular, the frequencies of the radiation emitted or selectively absorbed. However, Niels Bohr's atomic model has many limitations. The Bohrs model is applicable to hydrogenic atoms. It cannot be extended even to 2 electron atoms such as helium. The analysis of atoms with more than 1 electron was attempted on the lines of Bohrs model for hydrogenic atoms but didn't meet with any success. The fact that each electron interacts not only with the positively charged nucleus but also with all other electrons. Niels Bohr's model involves electrical force between positively charged nucleus and electron, but it doesn't include the electrical force between the electrons, which necessarily appear in multi-electron atoms. Also, Niels Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, but this model is unable to explain the relative intensities of frequencies in the spectrum. Bohr's model is unable to account for the intensity variations. It could not explain models for complex atoms. We have to use a new theory based on quantum mechanics, which provides complete picture of the atomic structure. In 1926, Louis de Broglie's hypothesis, together with Niels Bohr's early quantum theory, led to the development of a new theory of wave quantum mechanics to describe the physics of atoms and subatomic particles. And that is the end of our discussion. I hope that you learned something from today. Goodbye!